But welcome everybody to Science with Stina. Happy Monday, and hope you're all well on this lovely day. It's a pretty special day for this lesson, so thank you for tuning in. As always, we like to know where you're tuning in from, so if you could add in the comments where it is that you're watching and especially what students are watching with you. It definitely helps with our grants to report that we are reaching students during this weird and wild time. So hopefully we're all good with our tech now. Thanks again for joining us in a not sideways direction. That'd be kind of distracting. So glad we could get that figured out. So welcome, and we're gonna just pop right in. So we're gonna start with, what are tectonic plates? This is a pretty recent realm of science. I think it was discovered back in like 1912 and then maybe formally accepted in like the 50s and 70s. But it's basically how the Earth is moving in a way. So what I want you to do is I want you to imagine an apple. So you can close your eyes and picture in your mind maybe like Honeycrisp, or I really like opal apples, whatever it may be. Take that apple in your mind's eye and then chop it in half. I happen to have gone to the grocery store, so I have this apple here, so feel free to open your eyes again if you're still imagining that apple out there. But this apple happens to be a really great model for the Earth. Now, scientists, they use models all the time to represent reality. So obviously an apple isn't the Earth and the Earth isn't an apple, but I can make some pretty cool comparisons because I can look at the hard seeds in the middle, surrounded by this nice core holding them in place, and then the juicy fruit, and then this thin apple peel. Now, if I relate it to this fun little Earth model I have, they're pretty similar. So just like an apple, the Earth has a solid inner core, kind of like those solid seeds. Surrounding the inner core, there's the outer core, which might be like the fibrous core of the apple that I know a lot of people tend not to eat, although my dad definitely likes chomping in on those. And then there's the mantle. This is like the juicy fruit of that apple. And in real life, the mantle is actually liquid molten magma, so melted rock beneath the thin Earth's crust, which we might relate to that apple peel. And what's cool about this magma is there's actually convection kind of moving that magma around. So we'll get to why that's important very shortly. But to make this apple model a little bit better, I would have to take maybe a knife and scribble out on the peel, because the crust of the Earth isn't a perfect peel like this apple. It's actually broken up into different chunks, and those chunks are called tectonic plates. And I happen to have a map for you. Hopefully, maybe I can bring this closer. And this isn't your typical Earth map, but this is indeed the map of all the different plates that are found on our planet. And it's kind of like a jigsaw puzzle. So if I were to take that thin crust and break it into maybe big chunks or small chunks, that would give us a better idea of those tectonic plates. Looking at the map, I know I'm over here in Washington, so I'm on the North American plate. If I was in Canada or Russia or even Mexico, I would still be on this North American plate. So this is a huge tectonic plate that takes up all of that space. If I was scuba diving in the Great Barrier Reef, I don't know if anybody can see, I'm curious, what plate do you think I would be on? Can you identify the tectonic plate? Great Barrier Reef is of course off the coast of Australia, the east coast that is, and even if I'm not on the continent itself, I would still, sometimes there's a delay, so I'm trying to like milk it out a little bit, give you time to write in the comments. It's indeed the Australian plate. So whether I'm on the continent or in the ocean, I'm still gonna be on this nice little orange plate here. So what's pretty cool about these tectonic plates is that they're constantly moving. Now, I'm gonna set this to the side for just a moment because I wanna show you how fast they move. Are you ready? Look at your fingernails. Are they moving? Not very fast. They're pretty slow. On average, the tectonic plates move about as fast as our fingernails grow. So if in a week I were to check back, I could see, oh, my goodness, the tectonic plates have moved a millimeter or two. I don't know how fast your fingernails actually grow, but it's not very fast, or not very far, very fast. So it's a very slow movement, and if you're out there with your Oreos ready, this is a perfect time to get that in place, because we're going to do a little tectonic plate demonstration of movement, because they move in a couple different ways. So if you have your Oreo, I'm going to start with a fresh one. I've been eating Oreos all morning. Oops, you don't want a broken one yet. Okay, so you're gonna take an Oreo, and I kind of just like sliding it off the cookie, and then you're just gonna break the top part in half. We're now gonna imagine that that nice Oreo filling is that mantle layer. So remember the magma below the Earth's crust. And of course that nice cookie on top is our crust layer. And we can move this around in a couple different ways. So let me, when the camera's flipped, I'm like, oh, which side? Okay, so we can move it kind of side to side. Not actually side to side, because it's not like going like this. But one goes up, one goes down. If you're noticing, oop, there's frosting everywhere. If you want to eat your Oreo, you can also use your hands to do this. So your hands make great tectonic plate models. So you can move them against each other to demonstrate a transform boundary. A great example of this would be the San Andreas Fault in California. And so we kind of zoomed in on that map, and we have the North American plate shifting one way and the Pacific plate coming the other way. So if I had a lot of time on my hands, you could stand on one side of the San Andreas Fault, I could stand on the other, and we could wave to each other as we, at the speed of our fingernails, shifted on our way through the movement of those tectonic plates. Pretty awesome. Okay, so that's one way our plates move. Another way our plates move is they can shift away from each other. So this is a divergent boundary where I'm just gonna pull my Oreo apart, and as the tectonic plate layers are shifting away, that magma is gonna rise up and form a new layer of crust, and that's gonna be some of the areas where we're gonna have the newest rock forming in our world. So pretty cool. So shift those plates away, and you can think of an example of this as the Mid-Atlantic Ridge. This is absolutely on my scuba diving bucket list. Over in Iceland, there's a place where you can go scuba diving. Hopefully, I'm assuming we wear like wetsuits and hoods because it's cold water up there. But you can touch each side of a tectonic plate. So you can have the North American plate on one side, the Eurasian plate on the other, and I'm imagining I would try and push them apart and speed that movement up kind of sillily. But that Mid-Atlantic Ridge doesn't just cut through Iceland, it also runs all the way down the Atlantic Ocean. And so I think we like to make jokes that if you're gonna swim across the Atlantic Ocean, you should do it sooner rather than later, because it's always getting a little bit further apart coast to coast. So maybe now's the time. No, probably not. But that's that divergent boundary. So pretty cool there. Now, another way that our tectonic plates can move is they can crash into each other. I'm actually going to switch to a different model for this. So I'm going to... I have some ooey gooey magma. Okay, I don't actually have real magma. This is molasses. Real magma would be like melted rock, so thousands of degrees, not ideal for safe handling. But this nice molasses here is going to represent kind of that Oreo cookie frosting layer for you. And I'm going to use some graham crackers as my crust. We're just going to lay it on there. So again, we've talked about how plates can move side to side. We've talked about how plates can diverge. And then our plates can have convergence. I have a nice wet towel ready for my magma fingers. And in one case, you can have two tectonic plates, which are both continental. So for this example, I'm picking the Eurasian plate, sneak that down, and the Indian plate. You have two continental, I think they're called lithospheres, areas of that plate that are crashing into each other, and when they converge, whoops, we're gonna press, 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 and this is how we get mountains. And the tallest mountains in the world are indeed on the Himalayan mountain range. Mount Everest is out there, and that would be a great example of this type of a convergent boundary where, again, two continental plates are crashing into each other. Now, another thing can happen is if these tectonic plates are, say, a continental plate and an oceanic plate, so one has more continent on it and one has the weight of the ocean on it, when they come crashing into each other, the oceanic plate is heavier. It's got all that weight on it, and it's actually gonna slide underneath. And so if I were to take my sticky little hands and rub them together really, really, really hard, or even not that hard, you notice they start getting warm. And that friction that you're creating with your hands is similar to what's happening as these plates are rubbing together, and it's actually gonna melt the crust into new magma. That magma is gonna build pressure, and this is where I think the graham cracker molasses model is a little bit better than my Oreo model, because I'm gonna break that cracker to demonstrate as that magma builds pressure, we're gonna get, can you guess it? A volcanic eruption. Lovely. Let me wipe my hands off here. Yeah, the molasses demo is definitely fun. It definitely gives a pretty good idea, but it is a little bit on the messy side. All right, cool. So when that happens, that's called subduction. And as I mentioned, creates volcanoes. And Washington and Oregon and northern part of California really demonstrate this. So we have the Juan de Fuca plate, which is an oceanic plate, subducting under the North American plate. And as that occurs, we have the evidence of this string of volcanoes just along the west coast of the United States where that subduction is occurring. So Mount Rainier is a great example of that. And of course, we're doing this lesson today because today is the 40th anniversary of the pretty large and devastating eruption of Mount St. Helens. So we'll be talking more about that shortly. But I do want to mention, I just knocked my piece of paper over, that another kind of cool feature, in addition to those volcanoes, is also underwater. And the University of Washington does a lot of really cool research on the hydrothermal vents that are out along the plate where Juan de Fuca and the Pacific plate interact. And so there is all sorts of really cool science that we just are not going to have time to cover today when it comes to plate tectonics. So very cool stuff. I highly recommend checking out the UW website because you can actually watch some live underwater videos, because because they have these like fiber optic cable systems of these little research stations looking at these. And this is a picture of their poor, probably very expensive equipment covered in that brand new igneous rock from the volcano, actually erupting underwater and taking out part of their gear. So, you know, the hazards of studying volcanoes, I suppose. Okay, so that is plate tectonics in a nutshell. They're moving and grooving. We can review with our hand models. They're sliding against each other like the San Andreas Fault. This is where earthquakes are occurring. We have the divergent, where the mid-Atlantic ridge is. We have convergent, where we either make mountains or have subduction, and boom, you get volcanoes. So, with that, I'm pretty curious to know, maybe in the comments you can tell us, where were you on May 18th, 1980, 40 years ago? I personally was just a glimmer in my parents' eyes. Probably not. They were busy scuba diving out in Guam, having a great time, pre-kids. So if you don't have a memory yourself, this is my great homework for you, to ask somebody you know and see what they remember from this day 40 years ago. Driving over to Gig Harbor this morning, there was a great little news bit on the radio about a King 5 reporter and like their experience actually flying through the cloud of that eruption. It turns out that Mount St Helens is, let's see, here's our before and after of that event. And so Mount St Helens is one of many types of volcanoes that there are out there. There's things like shield volcanoes, which are kind of a low sloping volcano. Those are things where you find over hot spots, because if I think about our plate tectonics, there's kind of no secret to where those volcanoes are located. You may be familiar with the Johnny Cash song, The Ring of Fire. So all the subduction that occurs around the Pacific Plate, you find those volcanoes. However, in some places like Hawaii, you also get volcanoes, which are a result of hotspots, which typically make shield volcanoes, which are a little like lower profile. I kind of think of it like a warrior shield that I might set down to like eat a sandwich or something, take a break from war, and that shield would be really low sloping and it would have really fast flowy lava, whereas something like, I'm blanking on the name, it's gonna come to me, it's like a layer cake. Da-na-na-na-na. I'm gonna think of it. Anyways, volcanoes such as the types that are Mount St Helens, actually, I have it right over here. Composite is the word that I'm looking for. Composite volcanoes, like Mount St Helens, erupt more violently, and so we are going to actually do a little bit of a volcano demonstration today, but because of the type of volcano that this is, I know Mount St Helens also has another type of volcano as part of it called a lava dome, and then there's also another type of volcano called cinder cone volcanoes that they erupt with a lot of force, and when the lava, which would essentially be the magma that is now above the crest. So melted rock under the crest is magma, melted rock above the crest is lava, and that lava of a cinder cone volcano gets spewed so high into the air that by the time the lava hits the ground, it's already started cooling, which is called a cinder. So kind of put that together, there's a cone left behind by that violent eruption, and you get a cinder cone volcano. Composite volcanoes, these are the really big ones. When I say volcano, in my mind's eye, typically this is what comes to mind. So things like Mount Fuji or Mount Rainier, those are all good examples. And if I were to like chop this volcano in half and take a look, you would see that there's layers of rock and ash from the history of this volcano erupting over time. And I happen to have another cool model that shows kind of that composite nature. So if you would think of that word composite, I like to use it in art a lot, where I might take different things, layer them onto a canvas to make my masterpiece. A composite volcano is essentially those layers of different things that make this lovely volcano masterpiece. And because of the nature of this type of volcano, this is one that also has very extreme eruptions. And so Mount St Helens, being that is a composite volcano, had that experience within our recent human lifetime back 40 years ago. And so I'm seeing some great stories getting shared in the comments. Thank you all so much for sharing that. I think it's so interesting to hear what that day was like. But you can see from this picture that Mount St. Helens is completely different. It was completely transformed by this pretty devastating eruption. When you have all these nice glaciers, you can see that those melted, and a landslide that's caused by a volcano is known as a lahar, and that really ended up doing a lot of the devastation. I know it ended up closing I-5 because like the Columbia River was blocked with logs. It was getting under bridges, and just like imagining a river of concrete coming at you and taking out forests and trees and roads and parts of houses. Now, luckily, there were scientists out on Mount St. Helens, and they, could predict this. They noticed, I think it was back in March, that a steam eruption had occurred, and then, they're keeping track, noticing a bulge getting bigger and bigger. So, unfortunately, there's definitely a loss of life associated with this event, but it could have been a lot worse. And I think that's kind of a nice little cheers to today, where trust your scientists. They have your best interest at heart, and they really are, doing their best to understand these really complicated systems and keep us safe. So, kind of a nice maybe connection to today. So, Mount St. Helens, really kind of a cool story that please ask people about and find out what was happening on that day 40 years ago, because it is so interesting to hear these wild stories. So, of course, no volcano lesson would be complete without doing our own little, maybe, your typical science fair type volcanic eruption. So, I'm gonna shift over. I'm gonna put my model back together a little bit. And I'm gonna I have some baking soda. Now, if you don't have your own volcano model at home, that is totally okay. A cup and a plate will absolutely do. So we have some baking soda in this little vial here. I think a pretty nice addition to any science fair volcano experiment is a little bit of soap. This is gonna make it, I guess you could do an experiment at home. Notice what happens if I add soap to my baking soda volcano, and what happens if I don't add soap. I think it makes for a foamier, nice eruption. Next up, I'm gonna grab my red food coloring. That is shifted away from me. Just kidding, it's right here. I'm gonna just do a couple drops of that. Right, we're trying to represent the really hot temperatures of the lava that would be erupting from something like a composite volcano. Of course, a lot of composite volcanoes, they have more of what's called a pyroclastic flow. So that's that superheated ash and gases, or I guess that might be more like Pompeii's Pillar situation. But the ash from the Mount St. Helens eruption, really, like, I've heard stories about it blacking out the sky in places like Eastern Washington or Central Washington, and even, evidence of that ash circling the globe. So while definitely east of Washington got probably the most of that ash. It entered up into the atmosphere and circled around, so pretty wild event there. Well, definitely volcanoes can be pretty destructive. I know that ash is a great fertilizer for things, so also created, you know, land that we're living on today and even some of the air we breathe. So kind of some cool things to be thankful for volcanoes. Okay, once you have your baking soda, food coloring, soap mix, I'm gonna just set this into our volcano here. Kind of organize our space so that we are ready to add some vinegar. Now, I will, small disclaimer about this volcano model. We have our composite volcano, and we have a chemical reaction that we're using to, again, model or represent our eruption here. I talked a little bit about shield volcanoes and how they have this fast flowy volcanic eruption with pahoehoe lava that we'll maybe put a link in the chat to some very mesmerizing videos of that, because it's very cool to see. But I want you to kind of keep in mind that we might have a little bit of a maybe a confused volcano here based on our chemical reaction of choice being that I'm inside right now. So we might think of some ways to improve this volcano model, but let's erupt it first. So I'm gonna position that, and we're gonna add some vinegar and see what happens. Are you ready? Are you sure you're ready? I don't know if I'm ready. We're going in. All right. Amazing. Can imagine that I would think to improve this volcano model, I might add the Coca-Cola Mentos experiment, because for a composite volcano, I know that since they're known to erupt more violently, this eruption is pretty calm, it's pretty tame. So if you're doing a volcano model at home or for a science fair project, definitely look into making sure that your chemical reaction matches the type of volcano you're using. I think we should get a shield volcano model for this type of chemical reaction, or we could level up, take it outside and do that fantastic Coca-Cola Mentos where it just shoots into the air. I think that would be a little bit more accurate and improve our model. So that's kind of a fun thing you can always do with science is think about how models can represent a kind of scientific idea, and then what can you do to that model to improve it. And so if you're out there designing a cool volcano model, we'd love to see pictures or share some videos of you erupting a volcano of your own. So with that, again, keep sharing those fun stories of where you were 40 years ago, or maybe a story you know from somebody else who shared with you. I think this day is definitely, I've seen a lot of cool things on Facebook of people remembering with photos and all sorts of interesting things about that Mount St. Helens eruption back in the 80s. So with that, thank you all so much for joining us today. I included a donation link on this video that you're welcome to make a secure donation to Harbor WildWatch with. We also, if a monetary donation's not possible right now, we totally understand. If you'd like to share this video or other Harbor WildWatch content, like us on Facebook, like us on Instagram, social media. We're definitely out here providing all sorts of fun, free educational opportunities while you're stuck at home. So we're so thankful for you to join us, and appreciate your support however you can give it. So thank you so much, and I'm gonna eat the rest of my model Oreos here. So thanks again, and catch you later.